to this week's ITC Pizza Lunch. So last week we heard a talk on the theory of primordial gravitational waves from inflation or other things beyond the standard model. And this week is basically part two. We're going to hear the experimental or observational perspective. So speaking of observations, many people in the room are observational astronomers, and as such, observational astronomers are nocturnal for a few nights or a few weeks during the year. But our speaker today takes that to a whole new level because, of course, the experiment is at the South Pole. So if you stay the winter there, you're technically nocturnal for 6 months, which is fun. So let's see. So our speaker, of course, is John Kovac. He was got his PhD at University of Chicago before moving to Caltech as a Millikan and then Kilroy Fellow, and then joining faculty here at Harvard. He's been a Sloan Research Fellow and received the NSF Career Award. And of course, we'll see what happens next with the new generation of results. So take it away.
Okay, thank you very much, John. I appreciate it. So we had a really wonderful ITC Pizza Lunch series this semester. So thanks to the organizers for having this, very coherent sequence of talks, and particularly in the last week with Sarah Chandara's talk on the theory of generation of primordial gravitational waves, and also other talks that, not by accident, were scheduled over the last week and a half here at Harvard, including ones from Rob Caldwell last week, and just yesterday Dick Bond was down in physics. We've heard a lot now about the theory side of inflation and how constraints on primordial gravitational waves can constrain models of what happens in the early universe. So this talk is going to focus on the opposite perspective, the measurement perspective. And in keeping with the spirit of this great series, I really hope that this is completely informal, and I encourage you guys to interrupt me and ask questions as we go, rather than saving your questions for the end. So here we've got a picture of some of the telescopes that I'll be talking about. But to set the landscape here, this is a figure that we've seen in different versions, multiple talks this semester. We're going to be probing the gravitational wave spectrum with the CMB here at the very lowest frequencies, so essentially the horizon scales during inflation. I was interested to hear talks by Rob Caldwell last week that told us that in certain models, at least, the gravitational waves that could have been generated by primordial processes, the parity breaking models that Rob was talking about, generate not just unobservable levels of gravitational waves at the higher frequencies that are being probed by other techniques right now, but might generate spikes in observable amounts of gravitational wave power up at the megahertz scale. So maybe we need to make new versions of this plot and extend the x-axis a bit, and in a few years we'll be talking about tabletop megahertz gravitational wave interferometers. But for the time being, the focus is on looking for these primordial gravitational waves in the early universe sky, where they leave an imprint on the surface of last scattering of the cosmic microwave background. So the idea is that an inflationary process, which is our generic term for any accelerated expansion that sets the initial conditions of the universe at very early times, generates quantum fluctuations both in whatever scalar or effective field is driving the inflationary process, and also in the gravitational sector. And the gravitational waves that are laid down by that process exist in the early universe with their energy being diluted as the universe expands, but still being an appreciable effect, a much stronger effect at 300,000 years after the Big Bang than in the present-day universe. And so it can affect the dynamics of the photon-baryon fluid that is undergoing the phase transition from being an opaque plasma to a neutral gas at that moment in the universe's history. So if we, so the picture I want you guys to have clear in your heads of how the CMB becomes polarized in the first place at that phase transition is if you've got a free electron here in that primordial plasma, and as the plasma is recombining, expanding, cooling, and becoming largely neutral, the mean free path for scattering photons gets larger and larger very rapidly. And so the photon field that's impingent on one of these not yet recombined electrons starts to probe the local anisotropies of the density field. And so you start to see the inhomogeneities, very small 1 part in 10 to the 5 inhomogeneities in that photon baryon fluid. And it is the local quadrupole of those inhomogeneities as it's being sensed by that growing mean free path that sets up polarization of radiation. So the way that I like to think about this, the cartoon picture, is if you've got an electron that's responding to the electric field of the radiation, you've got stronger radiation coming in from the left or the right. The electric field is perpendicular to that, and it's shaking that electron in the vertical plane more than it's being shaken in the horizontal plane by the weaker radiation that's coming in from above and below. And so the net polarization of photons that are scattered out of the plane of the screen towards you, the present-day observer, out of the surface of last scattering, is going to be vertical. And so that effect is what drives the polarization of the CMB. It's a very weak effect. It's not a very efficient process because the polarization is only generated when that mean free path is growing and is probing these scales. So the typical polarization of the CMB due to density and homogeneities is only 1 part in a million. So that picture that I described that generates vertical polarization if I pick my electron at a particular spot along the mode that I'm depicting of density perturbations in the universe can only generate polarization that's either vertical or horizontal with respect to the orientation of a wave vector across the surface of last scattering. There's no handedness in the problem in the scalar density field that would pick angles other than vertical or horizontal with respect to that wave vector. And so that is capable of generating polarization patterns on the sky like this one that only represent half of the complete basis that's needed to describe an arbitrary polarization field on the sky, the so-called E modes. The B modes are the other half of that basis, and they are typified by patterns that have polarization vectors that are plus or minus 45 degrees with respect to the direction of the wave vector. And to generate such a polarization pattern, you need new physics. You need more than just one field, like a density field in the early universe. You need something that introduces a new direction to the problem and gives a handedness to the physics that's setting up this polarization. And so in the early universe, the leading candidate for generating primordial polarization in this B-mode form is gravitational waves. They do have a handedness, they have a polarization themselves, and if I'm clever about orienting the lobes of this quadrupole, which corresponds to the axes, if you've got a gravitational wave passing through the early universe, the surface of last scattering here, and I have the wave vector of that gravitational wave now carefully aligned so that it's coming out of the plane of the screen at an angle. And I'm picking, as you can see, not the plus, but the cross polarization of that gravitational wave. I can arrange so that the spatial direction on which space is being compressed and space is being expanded, orthogonally to that, project onto the surface of last scattering to give me an angle that can be plus or minus 45 degrees with respect to the direction, the k vector of that gravitational wave. And so you can get these B-mode patterns from gravitational waves. They also, of course, generate E-mode patterns. But what's unique about them is that they're capable of generating B-mode patterns, whereas the dominant physics, the density waves, are not. So the B-mode channel is really the clean channel for looking for gravitational waves and the polarization that comes from primordial processes. So if I add up a bunch of such waves on the sky, the typical patterns that I get from E-modes look radial or tangential. These are gradient-like patterns on the sky. And the B-mode patterns are curl-like patterns or typically have these swirls. Okay. I should stop and ask, is that all sufficiently clear, or any questions on this? Please, yeah.
You said the E mode is only one part in many, the two directions, the difference. Then what about the E mode?
That's a good question.
It's smaller, right?
It is lower, yes. It is definitely going to be lower, and I'll show you in a minute how low it is. In fact, I'll show you on this slide. Okay, so that 1 part in a million, the temperature of the cosmic microwave background is 3 Kelvin. So 1 part in a million would be 3 microkelvin. Typically, we represent the intensity of these patterns by their power spectrum. So we're squaring that intensity. So 3 microkelvin squared would be around, 3 microkelvin quantity squared is about 10, or 10 to the 1 on this axis here. So this is the strength of the E-mode polarization typically on the sky. So the B-mode polarization signals that we're talking about that come from primordial gravitational waves are going to be many orders of magnitude weaker than that. In fact, we can count down here and we can see that this curve here, which is drawn at a level which has now been ruled out by our data, is already 3 orders of magnitude in power below that E-mode strength. And the experiments, measurements that I'm going to be talking about are attempting to probe 1 to 2 orders of magnitude below this current level.
Can I ask a question?
Yeah, please.
I never thought about this before, but at the surface of that scattering, when all this is happening, the frequency is, what, 100 terahertz? Is that?
It's the, 100.
Resh just reminded me that redshift is like 1200 of the CMB.
The redshift is 1100.
1100?
Yeah.
So the frequency where this polarization is being set up is about 100 terahertz?
So,
Is that the right way to think about it?
100 terahertz.
I mean, we see the CMB now, it's 3 millimeters, right?
Mm-hmm.
What
Oh.
frequency was it at the surface of last scattering?
1,000 times higher.
Yeah, exactly.
So 100 terahertz, right?
No, that's right, yes.
Okay.
Yeah.
So I never thought about that.
Okay. I'm sorry, I was thinking you were asking a question about the horizon scale, but you're asking about the frequency of the light itself, yeah.
And, okay, so when you think about
It's
it,
optical, right?
Yes,
This
it's
is,
like microns, right? It must be,
yeah.
The temperature was 4,000 degrees.
okay, so this is really optical polarization, and we're seeing it now in the radio.
That's right, yeah. Yeah, the wavelengths have been stretched by that Z factor. Right, so this is, this, if you were able to observe it when it was being generated, it looks like the photosphere of the sun or any hot plasma.
Okay. It's interesting
Yeah.
to think about the scattering happening in terahertz, and we're observing it now. I didn't think of
Right. Okay, any other questions? Yeah, please.
So I should just know my vector calculus better, but so is it the E modes and B modes, if you have linear combination of different sources of the sky with some kind of spatial distribution, they don't mix, is that correct? Like, I mean, I can't add a bunch of E mode signals and get something that has that.
That is correct, yeah. No, they're a basis for linearly decomposing an arbitrary pattern on the sky. So if you start out with only E modes, you can't mix together any E mode sources and generate B modes. But so it's a very special thing that a scalar density field only generates E modes. That wouldn't be true of generally of point sources or something that has a anything that introduces a new preferred direction. Right, so you do need a second direction in the physics that's generating the thing. So a point source with a fixed linear polarization generates both E and B. Okay, so the other thing I wanted to point out on this slide, aside from the extremely low amplitude of the primordial B modes here, now measured in nanokelvin, in tens to hundreds of nanokelvin, is the fact that there is this lensing B mode signal that is expected to be there from the weak gravitational lensing of the dominant E mode pattern. in the sky. And you can see that it looks like a smeared out copy of the E-mode power spectrum that is peaking at angular scales here on this axis that are a few arc minutes, where the primordial B modes are peaking at angular scales multipole L of around 80, which corresponds to a couple of degrees on the sky, so larger angular scales here. And these lensing B modes come from the simple fact that as these photons that are starting their life as optical photons are traveling through the universe from redshift of 1,000 and being stretched out, they're also being deflected by the matter field. The weak gravitational lensing effect deflects every line of sight on order a couple of arc minutes with a coherent scale of a couple of degrees on the sky. And so it smears out these E-mode patterns and converts a small fraction of them to a B-mode pattern. So in this case, it's that extra field, the projected mass map of the universe, if you will, that's introducing a new direction to the problem, and it's breaking this E-mode symmetry. And there's rich physics in that field, too, and reconstructing it carefully can tell us a lot about the growth of structure in the universe. But for most of this talk, I'm going to be treating it as a source of confusion or contamination that needs to be removed to get at these primordial B modes. Okay, so the other source of B mode radiation in the sky comes from physics that has another direction, a handedness, is galactic foregrounds. They can generate both E modes and B modes. And at the lower frequencies, the polarized galactic foregrounds are dominated by synchrotron emission. So there it's the galactic magnetic field that is setting the orientation and allowing the generation of both E modes and B modes. And then there's the dust emission, polarized emission from dust grains that are again aligned by galactic magnetic fields, but have different spatial morphology than the synchrotron in general. And so up until recently, we've had very poor information about the polarized sky at high galactic latitudes in the very faint regions where we do these measurements. And so that's the other thrust of the talk and the challenges I'm going to be discussing, is that a lot of the effort that we're putting in now to these primordial gravitational wave measurements are characterizing the galactic emission signals so that we can do component separation. Okay, so just to set the stage for the progress that we've made here, E-modes were first detected in 2002 from a telescope at the South Pole. This is the DAISY telescope, which was an interferometer at that time. We're actually reusing the same mount now for the Keck telescope. So 15 years later, we're still getting good service from this mount. But this interferometer was capable of measuring polarization that was a few microkelvin on the sky, and this pattern that it measured in a patch that was about 3 degrees across is consistent just with pure E-mode polarization, plus a little bit of instrumental noise. So the WMAP satellite subsequently measured polarization on large angular scales across the sky. And so if we chart the progress in sensitivity of these generations of experiments starting from 2000, we can see that the raw sensitivity expressed in microkelvin of the telescopes is more or less following Moore's law. We are steadily marching down in sensitivity and in science reach on these experiments through different generations that we've now taken to calling stage 1, stage 2, stage 3. We're sort of at the transition from stage 2 to stage 3 right now. And I'm going to be talking at the end of the talk about where we expect to go in the future with CMB stage 4. And we can classify these, as I'll explain in a minute, by roughly the number of detectors of ground-based telescopes that are typical of each of these stages. And that really sets fundamentally the sensitivity of these experiments.
John, so on that figure, do you need the same sensitivity for all angular scales? Are all those the same angular scale?
So no. I mean, this plot is trying to gloss over the angular power spectrum reach of these different experiments, right? It's trying to collapse all of that just to a raw sensitivity. But these different experiments, Planck and WMAP, did have different sensitivities to different angular scales. And so do these ground-based experiments. And so really, if you want to do measurements that can constrain primordial gravitational waves, you need to have not just this raw sensitivity, but that raw sensitivity at the 2-degree angular scales that corresponds to the horizon scale at last scattering. At scales smaller than that, the gravitational wave energy density has decayed away already with the expansion of the universe before recombination. So that 2-degree scale is really the magic scale to aim for if you want to constrain primordial gravitational waves. It scales around this. So
you need a range as well.
you do, yeah. No, I mean, so certainly you would want to you'd want to map out the shape of this spectrum and convince yourself that it has this typical shape and not a shape that's typical, for example, of dynamic generation of gravitational waves in the early universe, which is another thing that could potentially be constrained, things like cosmic strains or defects, that sort of thing, would have a different looking spectrum here.
John,
Yeah.
you have that up. What thought, the telescope actually, I'm interested, what thought goes into the arrangement there? It looks like an organized randomness of sorts.
Yeah, no, there's a threefold symmetry. And aside from that threefold symmetry, the pairs of telescopes were placed to maximize the coverage of the UV plane, as you do within an interferometer. But that threefold symmetry was used for providing redundancy checks, essentially, for systematic control. And so that's another theme of the current experiments that I'm going to describe, that Boresight rotation that you can see this mount is capable of, rotating around its axis here, allows you to measure the same sky signals in 3 different receiver orientations. And that was an important feature of this experiment design and our current experiments. Okay. So to show you the diversity of current generation experiments, these are stage 2 and moving into stage 3 efforts now. And the range of angular scales that they're probing, the large dish experiments that are shown here are really optimized to measure those arc-minute scales where the gravitational wave, the gravitational lensing B-mode spectrum peaks. And of course, they are trying to push down to those degree scales as well with their sensitivity, although none of these experiments has yet managed to make raw sensitivity limited measurements at degree angular scales. But you can see 2 of these experiments here are at Atacama in the high desert of Chile near Alma. And the 10-meter South Pole telescope is our neighbor. It's attached to the other end of the building that the BICEP telescope lives in at South Pole. Let me show you now the BICEP telescope and the Keck telescope are in these observatory buildings at South Pole. And this is the spider balloon experiment that we're hoping to hear first results from their initial flight sometime this year. And the CLASS telescope, which is another small aperture experiment that is in Chile, using a novel polarization modulation technique to attempt to control systematics on degree scales from a site that's intrinsically less stable on degree scales in the atmosphere than the South Pole is. And so these are the telescopes that are really, because they have small apertures, have been optimized, targeted for the degree angular scales. And you can see there's a long list of other experiments here that I'm happy to field questions on, but I wasn't planning to talk about. Okay, so that's an overview of the current experimental landscape. Now I'm going to talk a lot about the experimental challenges that we face in trying to make these measurements in the context of our own program, the BICEP Keck program. And the experimental challenges we've already touched on each of the 3 I want to highlight through this seminar. Raw sensitivity, control of instrumental systematics, and the component separation problem. Okay, so I need to show all of the people who are doing the real work, the young people in our collaboration, the BICEP Keck collaboration. In 2 weeks, we're actually going to have this crowd plus everybody who we've accreted over the last year or so meeting here at Harvard for our annual collaboration meeting. But this was a meeting, this was 2 years ago? Right, yes. So this was our team as of 2 years ago. And you can see it's a fairly large team with 4 lead institutions and about a dozen other institutions that are now contributing to our efforts. So it's a mid-size experimental collaboration. So the approach that we've taken to try to give us an experiment that's well optimized for systematic control is to choose an aperture size that's no larger than is necessary to resolve those degree scale B-mode polarization signals that we're interested in targeting from primordial gravitational waves. And that allows us to place the entire experiment inside the cryostat, looking out through a vacuum window, the entire optics tube, and all of the readout electronics here up to the back surface of this Faraday cage are cooled to 4 Kelvin or below, and the focal plane is cooled to 300 millikelvin. So the telescopes initially used liquid helium for cooling. We now use pulse tube coolers, which are much more convenient than carting liquid helium to the South Pole. But the basic experimental philosophy has been unchanged since we pioneered this approach with BICEP 1 last decade, and it's been through multiple generations now that have been driven essentially by the evolution of the focal plane technology. So let's see. Let me show you that focal plane technology. So we've switched now to using these mass-produced superconducting detectors that are patterned on silicon wafers and produced by our group at JPL in the microdevices lab there. Since BICEP 2, Keck Array, BICEP 3, and now the BICEP Array, the next generation of our experiment, we've been relying on these detectors to allow us to scale up the detector count. The way that they work is every silicon wafer is patterned, as you can see here, into pixels that comprise arrays of slot antennas patterned in a superconducting niobium ground plane. And the electromagnetic field excites currents across each of these little slot antennas that are picked off by a microwave transmitting transmission line, a microstrip transmission line here. All of the vertical slots, you can see it better over here, are being picked off and going in one direction, and all of the horizontal slots are being picked off and going in the other direction. And the signals are joined phase coherently in a binary tree summing network, so that you have a phase coherent antenna array of one or the other polarization coupling to these two detectors. And these detectors are bolometers. They're simply heat sensors. The radiation comes in on this transmission line, is deposited through this gold meander, and gold isn't superconducting at these temperatures, so that's where the energy gets absorbed. Believe it or not, we used gold as a resistor. And so that thermalized energy then is read out with the superconducting transition edge sensor here. So any questions on the technology, these focal planes? Okay, so let me try to offer you just a fundamental argument for why the measurement that we're trying to make requires us to scale up to so many of these detectors. So you don't need very many numbers to try to make this argument. The observations that we're making, we try to make near the peak of the cosmic microwave background blackbody curve, around 100 gigahertz. And we fit these observations within atmospheric windows, typically 10 gigahertz wide. So think 10 gigahertz. And near the peak of a blackbody curve, the photon occupation number is of order 1. So in 10 gigahertz of bandwidth, you will typically have of order 10 to the 10 photons arriving every second in that bandwidth. So 10 to the 10 photons per second. And if with my experiment I want to measure the intensity of that radiation, the question I want to ask is, what is the rate of arrival of those photons? Now, if I naively assume that the photon statistics are Poisson, then my ability to determine their rate goes like the square root of the number of photons I've collected. So I can measure the rate of arrival or the intensity of radiation to 1 part in 10 to the 5 in 1 second. So the typical power that is coming in on our telescopes here includes the CMB and the atmosphere. The atmosphere is not perfectly transparent, even at the South Pole. So we see more than 3 Kelvin of radiations. It's of order 10 Kelvin typically. So 10 Kelvin's worth of radiation measured to 1 part in 10 to the 5 in each second would give you 100 microkelvin sensitivity per second of integration. And that actually works out, even though it was a very crude argument, that works out to be pretty close to what we actually achieve with our detectors. 300 microkelvin is typical. And so the fact that the photons actually obey Bose statistics, and there's some correlation between their arrival, is one reason for the degradation. There's also practical optics efficiency numbers, and a little bit of additional noise that's coming not from the photon statistics, but from the readout noise and the thermal noise of keeping this focal plane here at 300 millikelvin. We cool it to a level where that noise is subdominant, but it contributes a little bit. So 300 microkelvin in 1 second is the number that you can attribute to the sensitivity of one of these detectors. Now, the signals that we're trying to measure that were on that slide a few minutes ago, due to B-mode polarization on the sky, are of order 30 nanokelvin. So 30 nanokelvin, 4 orders of magnitude, if I'm getting this right? Yes, 4 orders of magnitude below 300 microkelvin in intensity. So that's 8 orders of magnitude in integration time, if you'd like. So 10 to the 8 seconds is how long you would have to integrate with one of these detectors to reach that sensitivity. So does anyone know how many seconds in a year? Okay, 3 years. Great, everybody's there. So 3 years, 3 detector years to detect 30 nanokelvin radiation in one patch of the sky. And a typical map might have 500 pixels that you would want to make that measurement over. And so we have 500 detectors in one of these focal planes, and if we had perfect observing efficiency in 3 years, we would be there. But the observing efficiency, practical numbers that we suffer from are actually pretty large. Of order 3 to 5 is the degradation in practical observing efficiency. And then there are other hits that are even larger when you go from raw sensitivity of this experiment needed to the need to separate out components now when those confusion signals become large compared to that 30 nanokelvin signal that you're trying to measure. So you can see that there's an argument already for an experiment that has many thousands of detectors, and as we're probing to 30 nanokelvin B mode on degree scales and below, very quickly the need for the experiment grows into the tens or hundreds of thousands of detectors to achieve this measurement in a practical amount of time. Was there a question back there? Okay. Yes, please.
Is it the deal with weather? Like when I go observing optically, clouds come in.
There's no weather at the South Pole.
That's why I asked.
No, so that's part of the observing efficiency hit. That number 3 to 5 of observing efficiency includes a lot of factors, but a relatively small portion of it is due to weather. We can really use 70 to 80% of the time at South Pole
So I figured
is good.
pretty efficient with that, but there must be some things that come up.
It's certainly going to be less than that at a site like Atacama, where they've got diurnal variations and a bad season and a good season. Yeah.
So, John, ground versus space. You don't have this 10 degree Kelvin.
Right. Right.
Is that the only difference?
Well, and you don't have weather.
Because you're trying to measure 3 degrees Kelvin anyway.
Right.
10 is not so much larger.
Right. So the per detector sensitivity in space can be 30 to 50 microkelvin root second.
Right.
Yeah. So it can be instead of 300. Yes.
300 on ground.
Right. So one detector in space is worth 100 detectors from the ground for the same amount of integration time, and then the observing efficiencies tend to be better too.
Right.
So you have to weigh against that the fact that it's very expensive to launch a cryogenic space mission, and cooling detectors. So WMAP achieved nothing like that sensitivity per detector because they were not a sub-Kelvin cryogenic mission. So to achieve that photon background limit, you really have to have your detectors running at exquisitely cold temperatures. You need an experiment of the complexity of Planck, essentially. Okay. Any other questions on the technology? All right, so the experimental strategy, I think I've already talked about a lot of this. The small aperture telescope approach allows us to have a cryogenic stable instrument, one that we can easily rotate around its bore site, as we were discussing. We can easily provide an excellent shield around the beam to soak up all of the side lobes, which is another dominant issue for the systematics. So it can be extremely well shrouded if we keep it small. We've optimized it to target the 2-degree peak of the B modes, and we integrate continuously from the South Pole, which, short of going to space, is the best place on Earth to get the maximum observing efficiency possible. And then programmatically what we've done is we've developed technology on one prototype instrument and then scaled it up to an array. And we've been through that several cycles at this point. So BICEP 2 prototypes that superconducting detector technology. And the Keck Array is now BICEP 2 times 5 receivers on the same daisy mount that you saw a few minutes ago. Okay, and so why do we need so many telescopes? Well, one reason, of course, is to just efficiently get a large detector count to get that sensitivity. But with the Keck Array, of course, with multiple telescopes, you have the option of having the telescopes observe at different frequencies, and that's critical for separating out the galactic emission. So what's shown here is the Planck data in all of the polarized bands that the Planck satellite observed in, and the all-sky maps that they made at those different bands. And you can see at the low frequencies, what's dominating these polarized maps is synchrotron, and at the high frequencies is dust and noise, frankly. At the high galactic latitudes, these maps are noisy, in fact, at all frequencies. And we're interested in trying to measure the CMB at frequencies like this, near the foreground minimum, at high galactic latitudes. So our own detectors are easily scaled to different frequencies, and we can build focal planes that have different frequencies. In fact, right now, we've deployed 4 different frequency bands to South Pole, and we're planning a 5th low-frequency band for, well, possibly for next year, but certainly for the year after. And that allows us to separate out the synchrotron and the thermal dust, which have different frequency spectra from the CMB. Okay. And so the data I'm going to show you as a worked example of how this works is the most recent published data, the BICEP Keck 2014 data set, where we folded in all of the information from Planck and WMAP, along with our own very deep maps at 150 gigahertz, and 1 season's worth of data from 95 gigahertz taken in 2014. So the 150 gigahertz maps, after long integrations with many thousands of detectors, did indeed achieve 50 nanokelvin in 1 degree patches in these maps. So these are the temperature maps, and the Q and the U show you the polarized signals. Over here on this side of the slide, these are null tests, consistency tests, where you folded the data back on itself to show the amplitude of the noise. And these actual null tests are consistent with our model of the noise. So 50 nanokelvin in 1 degree patches are 3 microkelvin arcmin is the units that are typically used in the field now.
John,
Yeah.
explain a little bit more about what that means. You fold the data back on itself.
So you split the data into 2 halves that are observing the same signal on the sky, and instead of averaging them together to integrate down the noise and to get at the signal, you subtract them. So you cancel out the signal, and you're left with instrumental noise and with any systematic effects that have entered differently in those 2 halves of the data. And so by judiciously choosing to split your data in many different ways, you can probe for all kinds of different systematic effects that might be entering into different portions of the data differently. So we call this jackknife tests. That's the jargon in the field, but they're null tests.
That's the jackknife test. Okay.
Okay.
And by judiciously choosing, you go a broad parameter space of how you split it up?
Every way that we can think of that gives us, a potentially different handle on how systematics might enter in. So, we have, I think, 14 different ways that are now canonical that we split the data. So things like splitting it in time or splitting it by instrument orientation are obvious ways to do it. You can split it by, detector position on the focal plane, whether they're towards the edge of the focal plane or the center of the focal plane. All kinds of different splits that hypothesize different ways that systematics might enter in, different parts of the data differently. So what you're left with is really, the inability to probe only something that enters in all the data all the time, just like a signal from the sky would. But you've designed your observations, and this is really important, going back to the bore site rotation, you design your observations to have as many different kinds of redundancy checks as possible. So you mix up the instrument and you reobserve the same sky signal.
So when you do these checks, and let us say there is actually a little difference,
Mm-hmm.
does that go into your calibration?
Well,
Or do you just say, oh, our experiment is bad?
we say, oh, our experiment is bad, and then we study it to figure out what the hell's going on,
So you don't
and we
just
take it
put
out.
an extra adjustable calibration parameter.
No, that's what you do at the end of years of work if you give up. Right? if you can't understand the effects in your data, then you include a fudge factor and you say
guys haven't needed to do that.
no.
Good for you.
No, and we haven't had to yet, and whether that situation is going to continue into the distant future is a very good question. It really depends on the details of instrumental design, and for example, Planck has been grappling with this very hard over the last few years for their polarization data at large angular scales, trying to get it to the level where they've analyzed it, filtered it, cleaned it up, so that when they do these null tests, these consistency tests, the residuals are consistent with just their noise model and nothing else, and they're not there yet. Okay. This is the 95 gigahertz data with just 1 year of observing with 2 of those receivers, so you can see that the noise is higher, 127 nanokelvin in degree patches. Okay, so I'm going to show you quickly what it looks like to analyze a data set like this. Now, so the BICEP 2 and Keck 2014 combined data set at 150 gigahertz only, and the black line here is showing the predicted signal just from the lensing, the known lensing BB signal. And you can see that the 150 gigahertz points lie well above that line, very significantly so. Look at the size of these error bars here at low L. So if we compare the noisier 95 gigahertz data, we can see that it also rises at low L, but apparently less than the 150 with much larger error bars. It's really the cross-correlation of those two frequencies that gives us most of the power and component separation at this point. And you can see the cross-spectrum here traces spatially correlated components between the maps and allows us to constrain the amplitude of how those maps are entering in differently at those two frequencies. And that's the basis of the parametric component separation approach that we follow, is we look at all of the auto and cross spectra between all the different frequencies that we've observed and the much noisier but very broad frequency coverage maps that we get from WMAP and Planck. This is just a wall of data to show you the raw ingredients that go into this likelihood analysis. The likelihood analysis right now, or I should say as it was applied to the 2014 data set, the last one published, has these parameters that describe the statistical properties of the dust and the synchrotron, their amplitudes, their frequency spectral indices, the spatial spectral indices that describe how red or blue they are spatially, the correlation parameter, the possible spatial variation of the spectral index that would come from probing different dust properties or synchrotron properties on different lines of sight is another parameter that has since been included since we completed the 2014 analysis. And I should highlight the work of Victor Buza from our group here, a very talented graduate student who's done a lot of the coding up of this likelihood model.
Can I ask a question? You've gotten now some of the parameters that are very important for you. When you now are analyzing your new data and your future data, will you be able to use this information to refine the analysis of that data, or will you simply have to start again and have these parameters re-emerge from the full data set?
So when we add new data, a new season's worth of data, first we analyze that data separately, and we do all of the consistency tests on that data that we would with any older data set. And once we've convinced ourselves that it passes all of these consistency tests, null tests, we fold all of the data together in one combined map and one combined likelihood analysis. At times we separately do the full likelihood analysis on the old data and the new data, and we see whether they return consistent parameters for all of these things. But ultimately, what you do is you want to produce a single combined map at every frequency of the sky. And then, yes, you repeat the likelihood analysis. It doesn't much matter, formally, whether you start your chains in high-dimensional parameter space from, the best fit model before, or you rerun the chains. But the point is you're folding all the data together.
It is interesting, though, because you do have the possibility that something that you derived in one set of data actually looks a little different, right, in another set of data. And then if that happens, how would you proceed?
Right, and so that would throw up a red flag, and we would work really hard to try to understand, what the statistical significance is of that inconsistency. We do many such tests as we fold in new data, and you've always got to keep an eye on the trials factor, because we do so many of these statistical tests of consistency, and the right number of them fail at the right levels, and that's generally what gives us the okay to proceed. Yeah.
In principle, we're talking here about astrophysics, and there are other data sets that give us information on that. So none of them is of good enough quality to supplement the data that we have about, there are dust maps from observing stars, from other sources.
Yeah, so I think the answer is no, but I'm not sure enough.
For H alpha.
Yeah, well, so H alpha, for example, has been used recently in our dust modeling, really to try to produce dust maps that have representative complexity, not really to produce templates that we can with confidence predict at any given spot on the sky what the dust polarization is, but just trying to make sure that our simulations of dust skies have the right non-Gaussian properties. So we've gone a long way towards using those kinds of data sets to build up multi-component dust models that are actually derived from three-dimensional models of dust distributions. But no, so I would be interested to know whether starlight polarization could really help us. But my guess is if the answer is yes right now, it won't be for long, because the precision of these data sets is marching along so rapidly now that I think that, the requirement is really to measure it at the frequencies that you need to remove it. And the modeling uncertainty of any extrapolation from other kinds of data sets is really going to exceed the requirements on component separation.
What is the spatial spectrum index?
So that describes the tilt in the angular power spectrum of these different foregrounds. They tend to be red. They tend to have structure on larger angular scales and less so on smaller angular scales. Exactly. That's right. That's right, yeah. Right, and so when you use real non-Gaussian models of galactic dust polarization, for example, that complexity goes into the simulations, but not into the parameterization in this form here. Okay, so let me show you the likelihood results, BK14 likelihood results, and I'll have to go quickly if we want to finish this up. But I don't have to show you everything. Keep interrupting me if you have questions. So this is showing the results for the key principal amplitude parameters are the primordial gravitational wave amplitude and the amplitude of the dust and synchrotron components here. And you can see that as we folded in one more year's worth of data, the BK14 data set, compared to the 2013 result combined with Planck here, the baseline, red, is the likelihood curve narrowed and shifted a little bit, consistent with the extra amount of data that was added. And the degeneracy of dust and R was reduced. So you can see that this ellipse is becoming more circular. And this currently stands as the best constraint on the amplitude of the primordial gravitational waves. This curve, while it peaks non-zero, doesn't significantly exclude zero, but its upper limit is R is less than 0.09. And if you combine it with the temperature constraints, you get a combined constraint on primordial gravitational waves of R is less than 0.07 right now. But the B modes are now driving the progress on that R. So I want to highlight now the progress we've made since that 2014 data set. So the 2015 data set has included a higher frequency that monitors dust, 220 gigahertz, and in 1 year's worth of observations, that map goes 3 times deeper than Planck did at that frequency. So that's the data set that's under analysis right now, and we hope we might have results for this month, but it'll have to be at least next month, I can say, because it's late in April.
Just a few days left.
That's right. And the uncertainty on R, which in the BK14 analysis was 0.001 024 is going to shrink to 0.019. Okay, that's the 2015 data set. And component separation is completely driving this. If we publish the data set that we worked with 2 years ago and had no component separation to do, that uncertainty on R would be 0.006. So the large factor between the raw sensitivity and the actual achieved sensitivity is the price that you're paying now for separating out the components, which include the galactic foregrounds and now appreciably the lensing signal as well. And so to remove that lensing signal, this is labeled with SPT pole delensing. Actually, that's a separate analysis that we have underway right now. And that could reduce the uncertainty on R at this stage of the data by only 10 or 20%. But in the future, that
means that at best, since your upper limit is 0.07, you can get the detection of 3 sigma at best. Right? Your sigma is 0.02.
That's right.
You can't do better than 3 sigma at the moment.
If it were to shift up to the 95% bound. That's right, yes. No, so one should not expect a significant detection in the result that we're about to announce. That's a fair statement. Okay. So this last line here, BICEP array plus SPT3G, is the forward-looking statement. The forecast reaching sigma R of 0.003. Let me spend a couple of minutes now talking about the challenges to get there in the future and how we're planning to get there and how the field in general is planning to get to those levels of constraining primordial gravitational waves. So the BK15 data set I mentioned included these 2 higher frequency channels, 220 gigahertz. So that's the new result that is going to be released shortly. Oh, and I've already said this, that those maps are 3 times deeper than the Planck map at that frequency. Just in the 2015 data set. In the 2015 year, we also deployed BICEP 3 at pole, and that's the prototype for the next generation of receiver. What we've done is we've scaled up the size of the optics by a factor of 2, and we scaled up the field of view as well. So overall, the throughput and detector count have grown by a factor of 10. And so BICEP 3 at South Pole, since last year when we deployed the complete focal plane, has had 2,400 detectors in one of these tubes, all operating at 95 gigahertz. You can see some of our students and postdocs working on the instrument down at South Pole. And the 2016 data set, last year's data, includes BICEP 3 at 95 gigahertz, plus more horsepower in the Keck tubes at high frequencies. So these are a slightly different frequency. We call it 210 gigahertz, complementing the 220s that are continuing to do their job. And the 2017 data set, so we just got back from South Pole and deployed these instruments and are beginning our winter observations now. We've included a higher frequency channel, 270 gigahertz, to help us probe the complexity of the SED of the dust and allow additional parameters to be constrained on the dust properties. And BICEP 3 is now operating at what we hope is close to full efficiency. And so it should be at least 5 times as fast as Keck receivers at a comparable frequency if it achieves its full observing efficiency, hopefully a bit more than that, closer to that factor of 10 I was describing. So here on one slide is an attempt to capture the evolution of different generations of our experiments from BICEP 2 to Keck Array, now from BICEP 3 to what we call BICEP Array, which is a new instrument that's going to be replacing Keck Array 2 years from now at South Pole. That is a custom-built expanded mount that's going to hold 4 BICEP receivers that are of this scale, that have focal planes this large. And you can see color-coded are the different frequencies that we intend to deploy. And it includes, for the first time, very low frequency 30 and 40 gigahertz detectors that are designed specifically to constrain the synchrotron. And that will probably be the first receiver that we build because the detector count is low in that receiver. And reaching multiplex factors to read out this number of detectors, now up to 30,000 detectors for BICEP Array, is one of the big technology challenges in this field. Okay, so here is a slide that's showing our forecast sensitivity to R, sigma R, as a function of calendar year, as we're deploying all of these frequencies. And you can see that as we march forward in time, these X's here are actually representing the published results and the preliminary result that should be published very shortly. And we are achieving that sigma R. And this top line here is for the full amplitude of the lensing confusion signal. And these other lines are assuming that we could delens or remove the lensing signal at different levels. And you can see that becomes increasingly important as we hit that lensing confusion floor in coming years. So that means that we're very motivated to jointly analyze our data together with large dish experiments like SPT, and we're working together with them actively right now. So the thing I want to mention briefly is that another big thread here, aside from component separation, is making sure that the systematics uncertainties keep up with this raw sensitivity. And so these are slides from Keck Array's thesis colloquium just last week, showing the current levels of beam systematics uncertainty. And the question that we're asking is, can we keep these levels marching down so that they stay well below the raw sensitivities or the statistical uncertainty on R here at the same sort of order of magnitude level that they currently are in the analysis?
Before we move away,
Yeah.
how is the competition doing? So there is the Simon's array and others. I mean, how far ahead are you?
Well, it's a hard question to answer because nobody else has actually published any results. So, I mean, that's an answer of a sort.
You know where they are.
Well, let me be clear. No one's published results at the degree angular scales that are relevant for constraining R. So they're achieving now quite impressive sensitivity at the arc minute scales. I wouldn't say observing efficiencies like we've been enjoying at South Pole. It's a much more challenging thing to achieve those efficiencies with large aperture telescopes. But I'm probably not going to say the aggressive statement that you might want to hear from me. But
No, I just,
well,
I want the truth, not I don't care if it's aggressive.
No, be aggressive, John. Go ahead.
Just tell me the truth.
It's being recorded.
you're right. So
Don't be polite. Just
I think it's very unclear, actually, how those other approaches are going to play out over the next 5 years of stage 3. And it remains to be proven whether or not they will be able to produce competitive results on degree angular scales. It hasn't been done yet. Nobody has shown that they can achieve detector limited sensitivities at those scales with other approaches or from Chile, right, or from other sites other than South Pole. And so we're way ahead in that sense, that we can make these forecasts by actually scaling from real analyses on real data and just basically dialing the clock forward by assuming that we're scaling our experiment up. Nobody's in a position to do that other than us at this point.
John,
Yeah.
can I ask you about the lensing? It's one of the components you have to eliminate, right, or subtract.
Right.
So what's the situation there? Do we know the shape with only an amplitude uncertainty, or is there a lot of uncertainty also in the shape of that?
No, there's very little uncertainty in the shape or indeed the amplitude itself, the power spectrum of the
Why should we
lensing.
have
Well, because
three lines?
it provides an excess sample variance. So if it's there and if it's at the full amplitude, we can debias it. We can take it out of the analysis, so it doesn't bias our result on R, but it adds extra noise, a noise floor, right? So you actually need to capture its morphology on the sky. You need to map it out to be able to remove it.
It's one realization.
That's the thing. We have some cosmic
Yeah.
variance.
Okay, it looks like I should wrap up. So I wanted to show you.
This is so interesting.
I wanted to show you the hard work that Kirit has been doing on what is one of the hardest systematics challenges in this kind of measurement, understanding how the beam effects, beam mismatch effects, enter as residuals after we've controlled all of the effects that we can easily model and remove from the data. What the residuals characterized with painstaking direct measurements of the beams in situ with sources at South Pole look like, tracing them through all the way to simulated analyses of the false B mode signals that they produce at each of the frequencies that we've made maps on the sky, and showing how well those average down when you fold in all of the detectors. And so we benefit from the systematics cancellation of Boresight rotation, which kills many symmetries that exist in these residuals, and also from the fact that we're folding in many detectors, and there's an averaging down effect there too. But Kirit has studied in great detail the limits of that averaging down, and he's working right now to forecast forward to see what the prospects are over the next 5 or 10 years, whether we'll be able to keep using the techniques that we're using to understand and remove these effects, and then keep the part that we don't understand as a systematic uncertainty that's subdominant to the statistical uncertainty in these measurements. Okay, so I want to say 1 minute's worth of stuff about CMB stage 4. For the last 3 years or so, this will probably be a little bit more than a minute. The last 3 years or so. The CMB community has been organizing around this notion that what we really need to do is build a much larger ground-based experiment than any one group can build in the coming decade, one that will have hundreds of thousands of detectors on the sky and hopefully make a definitive measurement. The Department of Energy has endorsed this as genuine high-energy physics. The P5 panel has put it on their roadmap, and now DOE and NSF have blessed this, this process over the last year by forming a concept definition team that's going to be reporting over the coming months back to the AAAC to propose a real project that we hope that the government will have funding for. That remains the uncertain part. But I think the good part that we've seen out of this process is that there have been a series of workshops where different groups have all come together now to really share our experience and to work together to form forecasts of how we can do in the future. Well, if we can afford to wait that long. But actually, you know, we feel like we're ready to go. So, yeah. So we're certainly organizing for that. But okay, so I want to highlight the fact that this collaboration produced a draft science book. A first edition came out last August, and it's available online. Just Google CMBS4. It's on the archive as well. And a second edition, as well as the concept definition team report, will be coming out sort of by the end of the summer and early fall. I should very briefly mention that CMB stage 4 does things other than measure R. It uniquely probes the parameter that we call N effective, so the effective number of light species that were present in the early universe. And it not so uniquely, but in a very complementary way, can also probe the sum of neutrino masses and dark energy, particularly early dark energy and its impact on growth of structure. Those are lensing-driven science goals. And right now we're learning as we go the ways in which the way that CMB lensing complements other large-scale structure surveys can help do things like break the degeneracies of these parameters, some of the neutrino masses, for example, with tau. So I wanted to highlight the fact that Victor, who again was responsible for that likelihood analysis on our real data, has been very engaged in the CMB stage 4 process. And so this is just a plot that I pulled from the public working group wiki that was an analysis that Victor posted last week. So you can see the total number of detector years. So we started with 3 detector years in that fundamental argument that I offered early in this talk. So now we're scaling up to 10 to the 5 through stage 3 and 10 to the 6 and beyond for the stage 4 efforts that we're projecting. And this is Victor's optimization for how you want to add effort at the different frequency channels and the delensing survey as we march up the effort to millions of detector years, march down the sensitivities of the maps, and ultimately what sigma r we can expect to achieve, assuming different things about the foreground complexity that we'll run into. And that's where a lot of the uncertainty lies at this point. But you can see that these sigma r numbers are frighteningly low. 10 to the minus 3 and below is what the science goal is for CMB stage 4. These analyses are guiding specific ideas about what the configuration for CMB stage 4 will look like. Okay, all right, sorry. So the march of experimental progress here. So the black points are achieved 95% upper limits. The red points are derived from those forecasts that I was showing you, which again are grounded in the current performance of our experiments making these constraints. So hopefully, with the caveat that we don't know the foreground complexity until we get there, hopefully these are well justified. So Sarah last week told us all about the theory of the parameter space that we're probing with these kinds of limits on R. But the thing I want to emphasize is that we've just started to rule out and probe the very interesting monomial models of inflation, and we're getting into an interesting theoretical territory that over the next 10 years we hope to get through, the so-called large field models that are typical of R of 10 to the minus 2 to 10 to the minus 3. So I'll just leave my conclusions up here, and thank you for your patience, and thanks to the organizers.
Well, there are plenty of questions during the talk, so unless anyone has something extremely urgent.
Well, is it possible to rule out inflation if you don't see it?
No.
Yeah, let's have some pizza. Thanks again, thanks John again.